recording this. Let's wait for this to load because I didn't save these slides. Um, I combined two appendices in one. So it looks like a lot, but I'm gonna be skipping through some of this, okay? In fact, let's just download this. Whatever it is here. Okay. And then download. There you are. See, it's a lot. We're gonna be going over some of this.
Oh my.
Wait.
So you said that's two of the appendices in the book, right?
Yeah, this appendix 3 and appendix 2.
Okay.
All right. And we need to talk about this so we can explain some of what you observe here, 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 right? So, all right. The quiz is not very, it's medium size, so we'll start at 7:30. All right, so you have a bit more than an hour. If you need to start earlier, let me know in the chat right now, okay? Because I can send you the quiz earlier via Zoom. It's easy to do. So what is when we talk about supernovas and we talk about what happens with the remnants of a dead star, we talk about, well, neutron stars and pulsars, and we were already talking about very dense objects, right? When I talk about very dense objects, I'm talking about objects where you see something like this. The same size, but more mass contained in the volume, right? What you are seeing there right now could be a comparison between a star, a low mass, a high mass, and then what happens when that high mass is contained in a very small volume, right? You can have a neutron star, right? Which gives you a much more bend or distortion in that rubber, right? That's because the density is proportional to the mass, right? And inverse proportional to the volume. So the higher the mass at a constant volume, so if on the same size, like the size of the Earth, you place the whole mass of the sun, you will start creating not a singularity yet, but it will be close to that. It will be a very dense point in space and time. And that's the title of this appendix. In fact, appendix 2 is about space and space-time only. And then we combine space-time and gravity because the fact is that we need to understand first what this is, right? In 1905, Albert Einstein discovered or introduced the whole idea of space-time and special relativity. And the main idea is that nothing can go faster than the speed of light, and that at the speed of light, time and length, they get dilated, and contracted respectively. So the whole idea of the dilation of time can be proved with a simple experiment. Let me see if I have it here. Oh, there it is. That's the one I always in a physics class. Yeah. So you see this person has a laser pointer, and there is a mirror there. So if the train is not moving, the light will go up and down, and you are outside, you are looking at it. So the reference frame will be inside the train. But now let's suppose if you are outside, so that's the reference frame has always it always needs to be a place where objects are moving respect to that reference frame. Now, everything is moving respect to any other object, right? For example, we normally say that the Earth, like for example, where we are right now, can be a good point of reference to study the motion of the stars. But guess what? Our planet is also moving. So there is not really a perfect reference frame or frame of reference. But for local situations like that, what you're seeing right now, being outside of the train can be a good frame of reference. And what you see is you see the light bouncing and coming back in that shape, in a triangular fashion. If you are inside a train and you have the laser pointer, you won't see that. You will see the light just going up and down. In any case, light is by symmetry, and by assuming the train is going at constant velocity, these paths are the same. And the thing is that you have a isosceles triangle in there. And on top of that, you know the height of this triangle is this. So in one frame of reference, you have the velocity of light times time. In another one, you have a different time because you should know, right? Let's show you this. From geometry, you should know, where is my shape? Where is stamp? Oh, I just draw it. You should know that a right triangle, the hypotenuse has a larger length than this, than the original length, which was the up and down motion. So that gave Einstein the first indication that light cannot travel, right? Light, even though light is going always at the same speed, right? These lengths are different due to different times. That is basically the roots of time dilation. There. You need to know the math, by the way. T prime and T are the different frames of reference. And here is your time dilation there. This guy here is called the gamma factor. Well, 1 over this, because T prime over this is T, right? So one is called the proper time, and the other one is your normal time. All right? So the proper time, which is this, is equal to the normal time divided by this gamma factor there. And I told you last class, right? This is irrelevant if v is the velocity of an airplane, a car, even a comet, or the Earth around the sun. V over c squared, v squared over c squared, becomes relevant for objects moving close to the speed of light. So we're talking about receding galaxies. We're talking about the jets that are coming from a black hole, right? Particles moving in the accretion disk of a black hole. That is when time starts being dilated. Or if we ever build, which I don't think, machines that can go close to the speed of light. That is when time dilation will take effect. Now, time dilation after a very, very long time can also be studied. For example, in atomic clocks. That was actually studied in the, I believe it was studied in the International Space Station. So what they did is that they had two atomic clocks synchronized. One on Earth and one was taken to outer space. And what they realized after some time is that when they brought them together on a lab, they were atomic clocks, you should know, guys, are synchronized to the, not even to the millisecond, to the hundredth of a second. All right, even more than a millisecond. So they've noticed that there was a very slight difference in the synchronization just by taking the clock to outer space. Not even to outer space, just orbiting the Earth in the ISS. So time dilation happens when objects are moving closer to the speed of light, but also when objects are away or embedded to gravitational fields, right? Let's go back to the whole thing about space-time then. So this perturbation that you see here, right? This distortion doesn't just affect space, but also the whole idea of space-time. All right, this. So space-time is the whole four-dimensional combination of space, X, Y, and Z, and time. That will be your four-dimension, which is, you can write it, X, Y, Z, and T. Okay. Okay. So the special relativity, guys, nothing can go faster than light, and when objects are traveling near the speed of light, time and space become relative. That's why it's called the theory of relativity. So a person moving in a spaceship will very easily measure a different time than a person that is static on Earth. That is the root of the twin paradox that I explained at the end of last class, right? One twin goes at the speed of light or closer to the speed of light to another star and then comes back. Time will run at a different rate, which explains why that twin will not become, time will pass much more slowly for that person. So then that means that for that person, it will be less amount of years than for the person who stay on Earth. So when Einstein combined, okay, let me actually tell you why he realized that there had to be something more, because that was in 1905. In 1915, he introduced the general relativity, that gravity is not really a force, but it's a distortion of space-time. But how did he realize, or why did he ask himself about gravity? Because special relativity is about speed, light, time, and frames of reference. So where did gravity come into the play? Well, let me tell you something. And I think I asked you this in chapter 4. Let's imagine this is the sun, this is the moon, and this is the earth. Oh, there you go, perfect. So what will happen if I remove the sun? That's what Einstein asked himself. So according to Newton, if you remove the sun, then the earth and the moon won't be able to travel around the sun. The gravitational force will disappear and they will go out of orbit instead of going around, right? But Einstein said something, hey, wait a second. Nothing can go faster than light. So this cannot happen instantaneously. That's when he realized that gravity cannot be a force. So the whole idea of the force of gravity is not really correct. He realized that gravity is a distortion of space-time, and that those distortions travel in gravitational waves at the speed of light. So for us to realize that the sun is not there anymore, it will take us approximately 8.5 minutes, because it will take 8.5 minutes for that distortion to become flat again. Does that make sense? Or did I lose anybody?
Professor?
Yeah.
Yeah, can you just explain that again?
So the reason why planets orbit around the sun are because of that. Just remember that video that I showed you with that professor showing how gravity works. So by bending space-time, planets go around that bent space and time. And they can orbit around the sun and moons around planets. What happens is that Newton's laws, unfortunately, will contradict the whole idea of relativity if we consider the gravitational force to be an instantaneous force. when Newton introduced the whole idea of gravity and the force of gravity, right? He said that that was a force that was acting between two bodies of different masses, acting instantaneously and being able to explain the orbit of planets around the sun. And well, we have Newton's law of gravity, which is perfect because we have been able to study it and to actually apply it to launch rockets to the moon and rockets to Mars and so on. But when you start going farther and farther into objects that go at the speed of light, or I'm talking about light in that case, right? Nothing can go at the speed of light besides light. So, or when we talk about objects that are going closer, traveling closer at the speed of light, Einstein realized that nothing can go faster than light. The whole idea of superluminical velocities is a misconception, all right? Back in the 60s and 70s, we were able to detect radio jets from galaxies, right? Due to supermassive black holes that are in the core of galaxies like ours. And apparently, they were going at apparent superluminical velocities. Now we know thanks to relativity, that's not the case, right? That's due to the point of reference that you are using. Okay. Special relativity allows you to correct for that, by the way. So nothing can go faster than light, not even gravity. So if the sun disappears, it will take 8.5 minutes for the light of the sun to stop reaching us, for the last straw or the last intensity of light sent by the sun before disappearing. So what we know is that the same time it takes for light to reach us, the same time takes for gravity to unbend. All right. Is that clear?
Yes, sir.
Yes.
Yes, so
Light,
gravity, if gravity isn't an instantaneous force, does it have a different new title? Like what?
yeah, general relativity though. Gravity is still a force, but it's not an instantaneous force. The electromagnetic force is still a force, but it never goes faster than light, the same with nuclear forces. So they're still forces, it's just that those are forces that are limited by the space-time in between.
Okay.
Okay. Light itself is limited by this gravity, by the way. Right after Einstein introduced his general relativity, in 1918, there was an expedition in the Africa, and there was going to be an eclipse. And what we know about eclipses is that we can, because during an eclipse, you can actually, if it's a total eclipse, right, you can actually see stars that are in the background of the sun. So a star that is located here, for example, when there's an eclipse, we can see it, right? Because the moon is going to cover the sun. What they were trying to test, one of the immediate results of general relativity, which is gravitational lensing. What is gravitational lensing? Is the whole idea that light gets distorted by gravitational fields. So light doesn't travel like this. Light will travel like this. Like that. So it's being distorted. And by that, we might be able to see stars in the background. By the way, that's how we detect black holes as well, by doing gravitational lensing and seeing how much light is being distorted. So light can be bent by gravitational fields. And the experiment was very rusty. In fact, They probably didn't really measure things properly, but their conclusion was yes, light is being distorted. Now we know more accurately that yes, light is being distorted, and we use those tools in astronomy and astrophysics to determine mass of black holes and the presence of black holes. All right. Okay. Those are the major ideas of general relativity. All right. Gravity arises from the curvature of space-time. Gravity slows time. That's very important to understand these guys and why some people consider them as time machines. When you are getting closer and closer to a black hole, time starts slowing down to the point where at the event horizon, which is the limit, right? Beyond the event horizon, we don't know what really happened. Well, we can infer what can happen, right? There is this whole concept of spaghettization, right? Of a person or an object falling and being totally elongated and then sucked into the black hole. But what we know is that time stops, right? And time stops because at that point, the escape velocity is the speed of light. So if we go back to that gamma factor, okay, that is slide is this one here. If we go back to this, right, which we can still use, if the velocity is the speed of light, this becomes 1 minus 1, 0. So the time dilation becomes infinite. That's the point where everything stops. That's the limit. All right. The other way you can explain it is by showing you this. Remember we talked about this? So light goes all the way and it never escapes, right? So you don't know what happens beyond the event horizon because there's no information coming out. So beyond the event horizon, what we think, besides the spaghettization, right, is that time starts moving backwards. Hence a time machine. Black holes are a consequence of general relativity, by the way. Right? So we know black holes were discovered in the 1950s, 1960s with the black hole in Cygnus X1 in the Taurus constellation. If you apply the concept of general relativity into stars, you get a black hole, which is a singularity. This is a consequence, this is a consequence of this. Because black holes can exist, the universe maybe, or now we know, is finite. It's not really infinite, right? The person who we owe that is Stephen Hawking. He was the one who related the Big Bang and black holes. He says in his famous book, The Brief Story of Time, that the universe started in the Big Bang and ends up in black holes. So they both are singularities. While one is the Big Bang, the other one will just be the opposite of the Big Bang, where everything might end, right? That was about the time when he thought that nothing can survive a black hole. So that's the information is lost, right? Later on, he retracted himself, right? Because he discovered the whole idea of Hawking radiation. And as you probably know, just like Michio Kaku and other scientists, Brian Greene, for example, and other string theorists, right? They allow or they accept the idea of extra dimensions or the whole concept of the multiverse, right? Which I'm going to explain later. So the fundamental assumption of the general relativity is that the effects of gravity are exactly equivalent to the effects of acceleration. That's the principle of equivalence, or the equivalence principle from Albert Einstein, all right? So what is that telling you? That's telling you that if you are in a spaceship, and there is a figure here, there, right? The way that you feel hovering in a gravitational field, right? And then you can compare it to the one by Al when he's in free fall through the gravitational field, all right? You can, basically, you can create an artificial gravity, right? This one is due to gravitational fields, right? And if you are just orbiting, you can feel weightless, right? And this one is due to the propulsion of the spaceship, all right? So someone who feels a force may be hovering in a gravitational field. Someone who feels weightless may be in free fall. Remember when I said how astronauts, or why do astronauts can levitate in space? That's because they are always on free fall when they are orbiting the planet, all right? As soon as you turn on the engines, you start, like, let's suppose you are actually far away now, and you turn on the engines, even here, right? You can very well create a whole idea, a whole artificial gravity, which allow you to actually stand, right? Um, so that's where this comes from, right? The effects of gravity are exactly equivalent to the effects of acceleration. So that's Albert Einstein, just in case you don't remember. And that's special relativity, 1905. He introduced the notion of space and time here. In the general one, he expanded to include gravity. He needed to, because special relativity by itself was contradicting the whole idea of Newtonian gravity. All right? So let's talk a little bit about reference frames. Actually, postulates of relativity. All right? The laws of nature are the same for everyone. The speed of light, okay, this is important. Let's suppose you are moving at half the speed of light, and you are moving towards a star. The second postulate tells you that regardless of your frame of reference, regardless of how fast you are moving, you will always measure the same speed for the speed of light. Okay? That can be shown using the gamma factor. And actually, that is a very strong, that has strong consequences. Before talking about the special relativity, with Newton, we had the Galilean transformation. So for example, if you are outside and you see a train, the train is moving at 20 kilometers per hour, and there is a person that is static. From your perspective, outside of the train, that person is moving at 20 kilometers per hour because it's moving together with the train. If the person starts running inside the train, you will measure the speed of the person plus the speed of the train. If you are inside the train, you will just measure the speed of the person moving. You will not add the speed of the train. So that is the whole idea of frame of reference. For light, that's not the case. There's no frame of reference for light. Light is the same for everybody. So if you are outside or inside a train and you shoot a laser, you will measure the same speed for the speed of light. That's why if two spaceships traveling at near the speed of light are approaching each other, they will not see a speed faster than the speed of light, which might be, according to Galileo, that would be a contradiction, right? Because you either add or subtract the velocities, all right? Okay, so again, relativity is going to force us to revise the whole idea of space and time, all right? Oh, that's the explanation I was telling you, right? If you're outside, you can see a person moving at an airplane, right? And you can see this ball not move. Okay, for this person, this ball is moving at 10 kilometers per hour. For this person here is moving at 910 kilometers. For this person, if you are in an airplane, you don't seem to move unless there's turbulence, right? You are like there. You can walk in the airplane, in fact, right? But for a person that is outside, it will seem like you are moving really fast. That is the whole idea of a frame of reference. All right. So everything can be measured by a frame of reference, by a reference frame. Einstein claimed that light should move at exactly the speed of light, which we label it C, in all reference frames. Now experimentally verified. You know where we, again, you know where we have verified all this? By studying black holes. Because by studying black holes and also dead stars, right? Supernovas, radio jets, gamma ray bursts, we have verified that regardless of where we look at, the speed of light of electromagnetic radiation is always the speed of light. It's always the same in vacuum, of course. So we have verified this. We have verified the whole concept of space-time as well, which we should go to that now. Let's see. So the time dilation, guys, again, you don't have to worry about the formula, but it's always important to realize that as you go at the speed of light, right? Time in the moving reference will go significantly more slowly. That's the important part. As you move closer to the speed of light, time in that frame of reference, in the frame of reference that is moving, will go more slowly, which explains the whole idea of the twin paradox. Okay, that's about time, but what about length contraction? If you have ever watched Star Trek or Star Wars, right? When the spaceships are about to move at the speed of light, you will see that the light of a star seems to be going towards the spaceship, right? So why is that? Because that doesn't have to do anything with time dilation, right? Here. So why is that happening? And we know this is true, by the way. This is actually based on relativity as well. This is due to length contraction. Time dilates. If time dilates and the speed of light is constant, what should happen with the distance though? Well, the distance, in order to keep, because you know, the distance between stars is not like, okay, how can I put this? When you go at the speed of light, because of time dilation, right? You are moving at a slow, from your reference point, right? You will be traveling at a much faster rate, apparently, but we know that's not the case. So something has to be made up for that. That is length contraction. So the reason why it seems like you are moving faster than light, even though you are not, is because length between the 2 points is being contracted. All right, and it's being contracted by the same gamma factor. All right,
But this is only for the speed of light, nothing.
this is for objects moving closer to the speed of light,
Okay.
which explains that picture I show you of this, right? So it looks like stars are coming to you because you're moving at the speed of light.
Right.
And you know nothing can go faster than light. So it will look like light is moving also towards you, like that.
And this is time and length contraction?
Time gets dilated, length gets contracted.
Okay.
Okay. What are the other consequences of special relativity? Mass increases, which is why I always tell people going at the speed of light is probably already a no. And the person who came up with the limit was Albert Einstein, right? We were able to break the speed of sound, but the speed of sound doesn't cause this, right? Mass increases proportional to that gamma factor. The faster you go, the more the mass increase. The limit is the speed of light. And that is the whole idea of E equals to mc squared. Energy or mass transform into energy because of this. If mass increases, what else increases? Momentum and energy. Okay. So unfortunately, that's already a limit. All right. There is no way, classically speaking, at normal motion to go faster than the speed of light. However, there might be shortcuts, right? Okay. Let's talk about some of the effects of relativity. Oh, by the way, here it is. Okay. So if this becomes 0, right, this will be, so the mass is the original mass divided by 0. That's basically infinite. All right. So when v approaches the speed of light, mass starts increasing and increasing. Okay. For a small b, that might be the case, but for b that is very large, this becomes energy. You know when we can actually test the prediction of the special relativity? In that Doppler effect. Remember what I said about stars moving away and moving towards the Earth? Who remembers that?
The wavelengths change depending on if it's coming towards you or away from you.
Exactly. And that was something discovered by Hubble. He discovered that galaxies receding from us, they are red shifted. And stars coming towards us are blue shifted. Okay. So let's talk about that and let's combine it with special relativity. So if you remember, the spectrum of visible light goes from red to purple, right? Purple, blue. Here. So the wavelengths are increasing here and increasing here and decreasing here. So the special relativity, right, tell us that as you move away closer to the speed of light, all right, there is time dilation. Let me ask you a question. Besides wavelength and the speed of light, what was the other property of an electromagnetic wave? So you had wavelengths and you had the speed of light. There were other numbers here. What were those numbers?
Frequency?
Frequency.
Yeah,
And what
I
is
was feeling
frequency?
Yeah.
What is frequency? You remember? 1 over
Frequency
time.
should be yeah, how the distance between wait, no, it's wavelength.
No. It's 1 over period, which is 1 over time. But wait a second. Isn't time affected by the speed of light? Yes. So the whole idea of Doppler effect comes from the idea that time hence frequency, are affected by the speed of the source. So in chapter 5, I gave you the idea of blue shift and red shift. Mathematically, now with the special relativity and that gamma factor, we can tell how much red shift and blue shift we should get. And that was done by Hubble. And he determined, right, how much each line should be moved towards the red due to the time dilation. So that is another way that we can test relativity. All right. We have tested relativity in different situations in astronomy. So astronomy tends to be the perfect place to study relativity, right? To test relativity. So now let's talk about space-time, right, guys? So it's nice that we understand the whole idea of the speed of light times dilation. Oh, by the way, here is the twin paradox. So for example, this is a journey to Vega, right? For a person that goes at almost the speed of light, may take 50 years to go and come back. For the person on Earth, right? It will be even more than that. All right. If you are traveling at the speed of light. But why? Because if you could travel at this speed, it will seem that it took you on 2 years. We're talking about biological clocks in there right now. All right. Now, why does it take much less than 25 years, which it should be at the speed of light? Because of length contraction. All right. If you use that gamma factor, you can find the length in between due to this high speed. So then it might take, biologically speaking, 2 years for you. But look how long it will take for a person who stay on Earth. 25 plus 20, 50 years. So you will be 2 years older. Another person will be, so you may actually not find your generation when you come back.
You will physically have only grown, like, aged 2 years. Like, it's not just like that it seems like 2 years to you. It actually is 2 years for you. Your body has only aged 2 years.
Your biological clock, your biological clock is affected by relativity, yes.
Okay.
Yep. Which is a problem as well when we talk about interstellar travel, right? Because even though we don't go at the speed of light, the effects of relativity can be affected if you are in a space for quite some time, traveling at very high speeds. Okay, let's start with space-time now and cube of space-time. A point, a line, a plane, a cube. So this is the one that you guys probably know, right? We live right now in your room, X, Y, and Z, right? Euclidean geometry deals with this, right? That's the geometry that you did in high school, right? Just the plane. Space geometry. But that's not enough, though. We don't only move in space. We also move in time. So here is all the dimensions of space-time. The 4th dimension will actually be time. Okay. With our technology, we have been able to understand that time can be dilated by gravity and by speeds closer to the speed of light. But you know, we can vary X, Y, and Z, but we cannot vary time like in a lab. One of the concepts that we deal is that if it's possible to actually change time, right? That's the whole idea of time machines. If it's possible to do that. Technically speaking, we probably will not. unless we talk about wormholes, which is coming as well. What is curve space-time? It's kind of geometry, but now we're talking about spherical geometry. So in curve space-time, you are allowed a bunch of different things. One of those things are spherical triangles, like you see there, where the sum of the angles is greater than 180. Where the smallest distance between 2 points is not a line, but a great circle, or part of the great circle, this one here. Where the circumference of a circle is less than 2 pi r. Okay. By the way, what are these two lines? Okay. In the plane, I can draw this, right? One line like this, and one line like this. So in the plane, those lines will never intersect. Like for example, two avenues, they never cut. But in space-time, in the curved space-time, in spherical geometry, two parallel lines, they can intersect at some point. All right. So there are different rules for that. In flat space, that's different than here. All right. Great circles intersect. And those are the ones that we use for navigation, for example. The most common one was what? The equator, remember? And we have the center of Earth, we live on the surface, and these are called geodesics, all right, that are used. If you ever talk to a pilot on an airplane, they use all these concepts of spherical geometry. They will tell you that the shortest path between, for example, two cities that they want to travel to are curved, are the geodesic, this one, from this point to this point, for example, right? They follow that, okay? Which makes navigation very tricky. You have to be careful, right? Because you have so many flying at the same time that, you know, nowadays with GPSs, we are able to determine all that. So for example, Beijing and Philadelphia. You can have this route along the 40 degrees northern latitude, or you can have this great circle route. All right. So by studying spherical geometry and understanding it, we can actually choose the most ideal and shortest path. All right. So yeah, parallel lines can cut. A great circle is the shortest distance now between 2 points. Okay. But remember, right? You can have different types of curved space-time. You can also have this hyperbolic sort of space-time, right? Where parallel lines don't converge, but they diverge. Where the shortest distance is actually hyperbola, not a circle, right? So you can have, for curved space-time, you can have different geometries, you can have different shapes. And that's what makes general relativity more complicated, because you have to deal with different geometries, all right, that can be caused by what? By gravity. Here is a picture I was trying to actually show you before, guys. The sun bending the space-time between planets and objects orbiting around the sun following that. Okay, so now we can imagine, right? If you take off the sun, I think that's what they do here. Yeah, so Newton view gravity as a mysterious action at distance, a force. But if I take off the sun, right? If I remove the sun, this bend caused by the sun will slowly by a minus and a half become flat again. Will become like this. All right. And that is when the Earth will be out of orbit. All right. So light also travels in that curve of space-time, which is why light cannot escape a black hole. Because when light enters, it just moves all the way to that singularity, which is the center of that black hole. Right? Now, why is the event horizon the limit? Because Einsteinian physics or general relativity can only take us to points where the speed of light is the fastest speed possible. Beyond the event horizon, the escape velocities and whatever is inside is traveling faster than light. And that breaks the whole concept of relativity. Now, does that mean that relativity is wrong? No, because Newton was not wrong. I don't want you to think that Newton was wrong, by the way. It's just that there are different layers that we have to cover. Newton works locally, and even when we study the solar system, or even galaxies. But when you go to higher order physics, to higher speeds, to higher densities, to singularities, that's when you have to start using relativity. But now we're going to exotic places of physics, things that we haven't been able to pan out beyond the event horizon. That's when we need another theory, which was the whole goal of Albert Einstein in his last years, which was also the whole of Hawking, which is the whole of physics nowadays. We understand this perfectly, by the way, but we cannot understand this yet. We know why this happens. We know what a singularity is. We know what the event horizon is. We know what a Schwarzschild radius is. We know how we can compute it. But we don't know what's happening inside a black hole. We don't know where the information goes. We know what happens with time, though. Time stops and then it slows down, it stops and then, right? And it has been taken by movies, right? Interstellar is one, right? Another movie that I think you guys should watch is Contact, which is based on Carl Sagan's book, right? In that movie, what they do is, well, basically they get the footprints of how to build a spaceship that will make a crack on space-time and will actually create a wormhole. And then the spaceship can fall into, because what you're actually doing, you are falling into that wormhole. And then you can travel, as I show you last class, in here, right? If we want to travel to Vega, and by the way, they use Vega, right? So in the movie, right, or in the book is actually better than the movie, by the way, because it gives more details about not just the science, but the whole environment, right? Because there's some politics as well in there. But the distance between the Earth and Vega is 25 light years. And what happens in the movie is that they detect a signal coming from Vega. And they are like, how is that possible if it's only 25 light years away? But hey, wait a second. We sent a signal to Vega almost 50 years ago. How? In the 1940s, when the first TV transmission was sent by the Germans, right? The first TV transmission sent in our planet was by the Germans when they inaugurated the Olympics. If you didn't know that, that's an interesting fact. That signal has been traveling in outer space in the 1940s. So now 60, almost 80 years right now. So they detected a signal coming from Vega. So then it took 25 years to reach the Earth because it travels in space. But then they wanted to go to Vega, and they got this idea. They so the aliens, right? They send them this, build a spaceship, and then they were able to break space-time and they go into a wormhole, right? Which is called the Einstein-Rosen bridge, because yes, Einstein allowed this to. A wormhole is a solution of Einstein's equations applied to black holes. If you apply Einstein's equations in black holes, you get a wormhole. It's a solution. And it's called hyperspace. Or as I told you last time, the fifth dimension, because you are going instantaneously. You are going faster than time, faster than light, from one point to another. Okay. Some scientists, they think that a wormhole may not just take you to another part of the universe. It might very well take you to another universe, another reality, right? And that actually makes sense, because since you are actually avoiding all this and you are traveling through time, you are technically going to an alternate reality. The whole idea of why time may not be able to be reversible is because as soon as you guys go back in time, you are basically creating another reality. That's the whole butterfly effect. All right. Maybe you have heard about this before. Let's suppose you go back in time and you stop your parents from ever knowing each other. What will happen to you?
Grandfather paradox.
What will happen to you?
Yeah.
Right? Okay, hint. You won't do it won't happen like in Back to the Future, right? You remember that movie, right? He went back and he screwed up, and then he had to make the parents meet again. Not really, that wouldn't happen. What we think will happen is that he will still exist in a reality where his parents never met. It's an alternate reality. It's an alternate universe. But how come he's there where he is an outlier in that universe? So that is very well. So what are other things that came up from relativity, gravitational lensing? Gravity allows us, because gravity bends light, we can use that to find very massive objects in the background of stars. For example, quasars, black holes, neutron stars. Now, I told you last class that we normally find clusters and binary systems, right? Hence, you can have two neutron stars orbiting each other. But they don't orbit themselves forever. Look what happens. They eventually merge in a big explosion. Why do they merge? Okay, you see what you see the animation there? Those are called gravitational waves. When two objects are orbiting between among each other, and these objects are very dense, like neutron stars, the space between them will be bent so much that there is enormous gravitational waves. It took us 100 years to discover something that Einstein predicted. That was Einstein's prediction based on general relativity. He predicted that objects, right, that the period of objects will eventually be reduced, right? The theoretical prediction is based on Einstein's equations, by the way. 1915, 1916. We discovered gravitational waves in 2014. Are there any questions?
Yeah, is this chapter gonna be on the final?
Some of it, yes. What can I ask on the final about this? Mostly about this, that what is gravity according to Einstein can be a question. Nothing crazy though. What is time dilation? I'm not gonna ask about the twin paradox, but that could have been a good question though. So what I can ask is to explain what's the difference between Einstein gravity and Newton's gravity. All right. List a few predictions from general relativity, black holes, the Big Bang, Doppler effect, gravitational waves. All right. And time dilation. Time actually is affected by gravity. All right. What else can I ask you? Oh yeah, what is a singularity? I can ask that. Actually, I think I should ask that. What is the event horizon? What is a singularity? Look at this diagram, right? That's a star, like the sun. This will be like a neutron star. That will be a black hole. So what's the difference between each of these? All right. And also, the question I always ask, I like to ask also in high school, right? Does light really get affected? How is light affected by gravity? That's the question I always ask. And you know what's always wrong? When they tell me that light is attracted by gravity. That is so wrong. All right. That, yes. All right. So how is light affected by gravity? So you may want to look at this. You may want to look at this. All right. Are there any questions?
I have
Yeah.
one more. Is this gonna be on the third test or?
Maybe. Yeah, I might give you a couple of questions so you guys kind of start reviewing for it. So the third test is next Tuesday, right? Yeah, so that will be chapter 16, 17, 18, this, and whatever we talk on Wednesday, which will be just the Milky Way. I don't think
Wait.
we'll talk about
Wait, the
cosmology.
test is next Monday or Wednesday? Because you said Tuesday.
Monday.
Okay, so it's
Actually,
Monday.
wait, no, you know what? Let's extend that. Let's make the test on Wednesday. So I can use the long lecture to finish some of the topics. All right?
So then so it'll be next Wednesday and then the final will be on Monday.
Yeah, we just have to do it like that. Okay?
Okay.
Yeah. So that will give us time Wednesday and Monday to finish all this stuff, because the only topic the only thing left right now is to discuss about galaxies and a bit of cosmology. Which
So we have
some way
chapter 19 and 20, right? That's 19.
But I'm gonna reduce that. So I want to reduce those slides a little bit, okay? I will repost them. We are kind of already talking about cosmology here when we talk about space-time, singularities, the Big Bang, right? Time dilation, gravitational waves, all that is cosmology. All this. So the thing is that now with cosmology, which by the way is the study of the universe as a whole, right? We can understand and we can test relativity. And so let me ask you a question. Based on all this was predicted by Einstein and is correct. Time dilation, gravitational lensing, black holes, right? Why we still call it a theory?
So with the concept like relativity, it is going to be very hard to like properly prove it, I would say.
What do you say? I didn't hear, sorry.
I feel like it's going to be very hard to proper. The reason why it's still a theory is that's very tough to properly prove this theory since it deals with something like way outside of like our control per se, say something like celestial on the celestial scale that would need like a couple of generations in order to actually take control of in a way so we can actually like prove it as a theory into like fact.
Well, the thing is that, well, let me ask you something. What about evolution and the Big Bang Theory? Which, by the way, they have substantial evidence. But there's something that you said that is true, though. We keep testing these guys. We keep testing relativity. We keep testing evolution. The best evidence of evolution are all those variants of COVID. Why do you think there are so many variants? Because the stupid thing keeps mutating, right? Because it's evolving. What about the Big Bang? The Big Bang, there's a lot of evidence. The Doppler effect, the cosmic microwave radiation, all this is an evidence of that the universe is dynamic, is expanding. But we can't keep testing it. So there is no problem in science to keep things calling them theories. Now, why do we call Newton the law of gravity or Newton's laws? Because when Newton came up with that, there was not, like you said, a celestial scale to keep testing it. There was just a local environment, horses riding or people riding horses or cars or just that, right? So that was the war for them. Nowadays, we have a bigger picture, so we can keep calling things theories now. All right. All right, guys. So that is basically what I wanted to go over with this. Are there any questions about black holes, or is it more clear now what a black hole is and what it isn't? By the way, black holes are not vacuum cleaners, all right? Let me actually go over that because that's something else that I need to go. Okay, that's the sun. Let's suppose instead of the sun, I remove the sun and I put a black hole in there. What will happen with the Earth? You can say what you think, and then I will tell you why it is. There's no problem, all right? So the sun becomes a black hole right now. What will happen with the planet?
Will it just continue to rotate until it starts to slowly move inside the black hole?
Yeah, not much really. Like if the black hole just turns to a black hole right now, nothing really would change.
Except we will freeze to death.
Exactly. Yeah, basically nothing changes.
So the Earth will keep rotating. You know why? In order for material to be sucked into the black hole, you have to be beyond the event horizon.
Okay.
So black holes are not vacuum cleaners. Lucky for us, because if they were, right? So they are not. They just affect objects that get very close. That's why there is a whole accretion disk surrounding them. All right. Okay, so that's another misconception. What else?
Professor, I just have a question.
Yeah.
Do we know why that's a misconception? Like, why do people think that black holes are like a vacuum cleaner? Like, is there like someone who predicted it?
No, because of pictures, movies, because of what they read in books, right? There are movies that they show you that. For example, if you watch Interstellar, actually Interstellar does a very good job on that. But if you watch any other movie, or they will tell you, oh, a black hole, right? And then they will look. When I was a kid, and you probably want to laugh about this, but that is when I got into astronomy, because there was this magazine that my dad was reading, and it was talking about black holes. And there was a science fair in school. So I said, I want to do my project about that. And we did a nice thing, right? And yes, I even saw when I was doing that, oh, what will happen if we go to a place where there's a black hole? We will get sucked into that. But then I talked to, it wasn't an astronomer, but we went to an observatory. And then he explained that that was a misconception, because that misconception comes from the whole name, black hole. And also from the misconception that light gets sucked into a black hole. Light doesn't get sucked into the black hole. What happens with light is that when light gets into the path of the black hole, it gets into this spiral mode. But if there is light going around it, here, but if there's light going around, it can just be bent, right? Light can be bent by the black hole. Here, see? If light goes too close to the event horizon, it will then go into the distortion caused by the black hole. So light travels in a space, and the space around a black hole is totally distorted. Hence, a black hole. You know why we call it black hole? Because nothing comes out of it. That's why. Is that clear or not?
Yeah, no, that makes sense. I just was like, you know, because like you said, it's like portrayed in movies that way and stuff like that. So I was just wondering, like, you know, how things change over time. So I was just wondering if there was like someone who predicted that that's what black holes did, and then they found out that that's not what it did.
Well, something that has changed in the last 30 years, 20, 30 years, because was the whole idea of Hawking radiation. Because with the whole discussion about the information, what happens with things going to a black hole, there was this idea, what happens with black holes themselves? Are they everlasting? And what we know is that they evaporate. They take trillions of years to evaporate, depending on the mass and size. But as they start shrinking, they start evaporating faster and faster. So the Hawking radiation predicts that. The Hawking radiation is just that a particle and an antiparticle in the universe are always created, formed, and then they auto-annihilate each other. But what happens if that same phenomena happens in the event horizon? That's what Hawking asked himself. Hey, what happens if that doesn't happen here, but here? One particle will go away. The other one will get sucked into the black hole. So that particle that left and that wasn't annihilated by its antiparticle is radiation that is technically being ejected from the black hole. By doing that, the black hole starts losing, I don't want to call it momentum, but mass, slowly and slowly.
So that's what helps with the evaporation of it?
Yeah,
like,
until it evaporates.
Oh, okay. That's interesting.
Yeah, and the thing is that that should have been Stephen Hawking's Nobel Prize. It's so unfair that he didn't win. It's sort of it's almost as like, you know, but we know that happens in the universe, right? Anyway, do you think black holes can be created in particle accelerators? Maybe, right? In the Large Hadron Collider, for example, if you go into the news of 2011, 2010, there were some scientists, not even people, there were some scientists who were very concerned. Because do you know what we do in the LHC? Have you ever read what we do in there?
No, I'm not sure.
So the LHC is colliding hadrons, very energetic protons. So energetic that they can recreate the Big Bang. So what we're doing there is we're trying to recreate in a very microscopic level the conditions of the Big Bang. But wait a second though. Have you ever heard about primordial black holes? So what we think is that when the Big Bang happened, there were black holes created by that enormous amount of energy and magnetic fields. So there were cracks of space-time being formed. That makes sense. So scientists were concerned, hey, wait a second. If you do that, you're gonna create a micro black hole in the LHC, which eventually will become bigger and bigger and will suck the whole planet. nothing happening, right? I mean, the reason why we think, or no, the reason why we know nothing happens is because of Hawking radiation. Those black holes evaporate instantaneously. How about that? Right? So that's science to the work, right? We're planning to build a more powerful one, by the way. The US is a candidate, but again, you know, we don't know because we have to find a location for it. The LHC is in Switzerland and it's very, very big. There is one here in Chicago called the Fermi Lab, but I would really, really like if they are able to make one in the US, another particle accelerator as bigger or bigger than the LHC.
So will that be like a multi-country project where multiple
It
countries?
should be at this point. Nothing in science can be dealt just by one country, because it's so expensive. And also, in these projects, you have scientists from everywhere, not just from the US. You have Canadians, Japanese, Korean, European, right? So they all have contributed. I always say that science doesn't have boundaries. You can have a Jewish person working with, like, also, yeah, it's true that many of the scientists are agnostic, like, that's true, right? But you can have a Jewish scientist working with a Catholic one or with a Muslim one. Easily, they don't care, right? Because they're
I think
working
it
with
brings
God.
different perspectives too, especially like different countries, like, you know, especially like when you're viewing the sky, you see so many different things in different countries and things like that. So it helps bring different perspectives and different ideologies too. So I think it would be helpful to a project for it to be multi-country.
Yeah, it would, like, for example, the James Webb Telescope, right? The only countries that right now are kind of iffy, I don't have to say it, right? Russia and China are in their own path. Although, when it comes to research, we work together with them. So, for example, I have worked with Russian scientists and Chinese as well. But when it comes to NASA projects, you should know that NASA is run by the, it's under the federal government, right? So that's when politics get into the way, though, so that you cannot. But there is a big but, though. Wasn't the US using the launching from Russia a few years ago?
Yeah, I was gonna say, I feel like Russia and like the US working together with certain things was definitely something rather recent that I heard about.
Yeah. So luckily for these type of things, we leave politics aside. Anyway, guys, so I will start taking the attendance before the exam or before the last quiz. This lecture was recorded, so